Today, we are going over exponential functions.
Here are some vocabulary words that you need to know in order to understand exponential functions. What is an exponential function? It is a function of the form f of x is equal to b to the power of x, where the base b is a positive constant other than 1 and the exponent x is a variable. Exponential functions have asymptotes, which is an undefined line where the graph gets closer and closer to, but never intersects. Growth and decay means whether an exponential function increases or decreases based on its b value. The base e is the base of the natural logarithm written as ln x. Y equals ex is called the natural exponential function.
We will be covering these key concepts that have to do with exponential equations and functions.
When we graph, we always start by creating a table of values using the parent function. Then we apply the transformations. Once I have these numbers, I will simply plot the points and draw a smooth curve. Let's try to do an example problem. F of x equals 3 to the power of x. We start by creating a table of values. Since this is already a parent function, we have no transformations to apply. We can just go on and plot the points and draw a smooth curve. We always want to label and draw our horizontal asymptote, which is located at y equals 0. These are the key features of the graph. These characteristics will always be the same for the parent function, regardless of changing the base. Transformations. The rules of transformations are the same for every type of graph. A is a vertical stretch or shrink by a factor of the absolute value of A. If A is still negative, a reflection across the x-axis. If your x is a negative, that means reflect across the y-axis, and so forth. Let's do an example. F of x equals 3 times 2 to the power of x plus 2 minus 5. Let's describe the transformations. When we do so, we describe them in order of the operation. So I have a horizontal shift to the left by 2 units, a vertical stretch by a factor of 3, and a vertical shift down 5 units. Let's graph. We follow the same steps. We make a table of values, apply transformations, and then graph a smooth curve. As you can see here in the parent function of table of values, you can see that the horizontal asymptote is located at y equals 0. When we applied transformations, we had a vertical shift down 5 units. Our horizontal asymptote will also shift down 5 units as well. So in our new table of values, our horizontal asymptote is located at y equals negative 5 now. So now if we have our values, we can graph our smooth curve. Always label your horizontal asymptote as well, and these are their key features.
Exponential functions can either have exponential growth or exponential decay. If the base of the function is greater than 1, it has exponential growth and the growth rate r is b minus 1. However, if the base of the function is between 0 and 1, it is an exponential decay function and the decay rate is 1 minus b. Try these examples. Identify a and b. Since f of x is equal to 7 times 0.9 to the x, a is equal to 7 and b is 0.9. Since that's between 0 and 1, this is an exponential decay function. Next, f of x is equal to 4 times 1.35 to the x. A is 4 and b is 1.35, which is greater than 1, so this is an exponential growth function. When dealing with exponential functions and equations, you should understand the basic exponent rules. These include the product of power, quotient of power, power of a power, power of a product, power of a quotient, zero power rule, negative power rule, and fractional power rule. These algebraic rules are needed when you solve exponential problems. The base e refers to Euler's number, which is approximately equal to 2.71828. It's a rational number, and the natural exponential function that uses base e is y equals e to the power of x.
The inverse of a function is what results after switching the input and the output of a function. In order to find the inverse of a function, the first step is to convert f of x to y if it has not already been done. Then switch the x and the y variables and isolate y. Remember to change y to a y to negative 1 to signify that it is an inverse of a function. Let's try it out with the exponential function. We have the function f of x equals 2 times 3 to the x. Switch the f of x to y. Switch the x and y. Isolate the base by dividing both sides by 2. Then use the inverse relationship between exponential and logarithmic functions to finally isolate y. Remember, the y of negative 1 is to show that it is an inverse of a function.
To solve exponential equations, we must either find a common base or use logarithmic properties. To find a common base, you need to rewrite both sides using the same base so that you can set the exponents equal to each other and solve for x. Here we have this exponential equation. Since 9 and 27 can both be written with a base of 3, we can rewrite 9 as 3 squared and 27 as 3 cubed. Then, using the power of a power rule, we can multiply 2 by x minus 2 and 3 by 3x. And now we can set the exponents equal to each other. And then solving for x, that'll give us x is equal to negative 4 over 7. Sometimes you cannot find a common base, so you can use logarithmic properties to solve. Apply a logarithm to both sides, use the power rule of log, and rearrange the equation to isolate x. In this example, we apply a logarithm to both sides. We can use the power rule of log to get 2x minus 1 log base 3 is equal to 2 plus x log base 7. Using the power rule of log, we can bring the exponent down and simplify further. Then, using the product rule of log, we can isolate x and find the final answer. X is equal to log 3 plus 2 log 7 divided by 2 log 3 minus log 7.
How do we solve exponential inequalities? Step 1 is, if necessary, we utilize the critical numbers concept and then test the number line to see which intervals satisfy. We will then state the solution. Let's do an example. In this case, we will utilize the critical numbers idea by changing the inequality sign to an equation sign. Then we will have the same base exponent, so we can set the exponents equal to each other. X equals 5 is my critical number. We'll then use x equals 5 to test the number line. We'll pick a number to test. Let's use 4 and 6. We will change our original inequality by subtracting 27 to both sides. Use critical numbers and we get 3x minus 2 minus 27 equals 0. When we write it this way, we can see if our number is positive or negative. We substitute in 4 and we get a negative. We do the same thing with 6 on the other side. Our solution would be x is greater than 5.
How do you solve exponential word problems? Here are the steps. The very first thing that you need to do is to figure out whether the word problem is asking about exponential growth or decay by looking at keywords that indicate whether it is a growth or decay. Then you have to select the correct formula and understand what the variables represent. After you get the formula, you match the values given to the variables in the formula. Now that you identified your formula and labeled all your values, you substitute the numbers into the variables, and this creates the equations you need to solve. Lastly, you solve the equation for the unknown variable by isolating it.
How do we graph an exponential growth? We need to follow the steps of graphing exponential functions. These steps included to make the table of values of the parent function, apply transformation, graph the smooth curve, and identify characteristics. We first need to make the table of values. We want to plot the points -2, -1, 0, 1, and 2. Then we apply the transformations of the function. You can see here the transformations are in orange text. We will get these values. As you can see in the parent function, we have a horizontal asymptote at y equals 0. Since we have a shift of 8 units downward, the horizontal asymptote will also be shifted 8 units downward. So the new horizontal asymptote will be at y equals -8. Now we simply graph. Always remember to label and draw your asymptotes. These are all the characteristics of our graph. When we identify x-intercept and y-intercept, we do not want the decimal value. We can only use the estimated value when we need it for graphing. When asked for intercept values, we need the exact values. So we need to go through the evaluation process to figure that out.
Let's try solving an exponential equation. Take a look at this problem. We first need to isolate the exponential expression, so we divide by 4 on both sides. Now we can see that we do not have a common base, so we need to solve it by using logarithms. We'll rewrite this into log form, and we use the natural log because the natural log and e to the power of x are inverse functions. The base input 0.1x becomes the output, and the output 15 becomes my input. Now we isolate x, so we divide by 0.1 on both sides. This is your exact value, and when we put it into the calculator, we get approximately 27.1. After solving the equation, we need to substitute the answer back into the original equation to make sure it is a true and valid solution. After substituting it, we simplify, and we can see that they both equal each other, which makes the solution valid. Since it is valid, we know the solution works and is not extraneous.
Take a look at this word problem. So for this equation, we are looking for the time it takes for the amplitude of 0.75 millimeters to reach 0.1 millimeters. The problem states that the amplitude shrinks by 25% every second, meaning that every second the vibration is only 75% of what it was the second before. So we start with the initial vibration of 0.75 millimeters. Every second, multiply the amplitude by 0.75 because the string loses 25% of its strength per second. We want to know how many seconds of shrinking it takes until the vibration becomes 0.1 millimeters. So we set the equation equal to 0.1 millimeters. We then take the log of both sides to bring down the variable t, which is what we are looking for. We then could apply the power property of log and move the t to the front. Then we divide log of 0.75 to both sides to isolate the variable t. We then get the exact, or can further simplify and estimate that it takes 7 seconds for the amplitude to drop from 0.75 to 0.1 millimeters.
Thank you for watching the exponential functions video lesson.